Around 80 million years ago, the continental block of Iberia collided with the rest of Europe, that's France, to go on to form the mountain range of the Pyrenees. And in the process, elevated rocks of the continental crust that tell of much older tectonics, the Variscan origin, some 350 million years ago. But we don't have to go into the mountains. These rocks come down to the Mediterranean coast at the Costa Brava to provide a window on how rocks deform when they are hot. There are some dramatic rocks that tell some surprising stories.
Well, this is one of the world famous sites in structural geology. It's the Cap de Creus, and it's a place to come and look at deformation of metamorphic rocks and igneous rocks together, these pegmatites. So let's explore around this neighbourhood and look at some of the fantastic structures there are to be found on this rocky promontory.
The area is protected, a nature reserve that limits access and stops the tourist development that characterises much of the coastline nearby. Geologically, much of the reserve is made of metamorphosed sedimentary rocks. That were caught up in the Variscan orogeny.
So of all the rocks at Cap de Creus, these are the ones that have experienced amongst the highest temperatures, the most extreme metamorphic conditions. These are pegmatites, these light coloured seams, they're called leucosomes. They represent patches of partial melt from the original metasediments here, sort of frozen in action. They're not escaped out of the rock, they're frozen into it, and they're rather nicely deformed into these nice little fold structures. So high grade rocks. And it's not just the folding that tells of the deformation here. In fact, that's just a sideshow. If you look at the aggregates of minerals in this, they're intensely strung out. Really intense distributed strain throughout this pegmatite complex. So lots of deformation.
So these are pegmatites, and their minerals record the peak metamorphic conditions of around 500 degrees Celsius and around 3 kilobars pressure, which is equivalent to about 8 or 9 kilometers down in the crust. And this all implies a very high geothermal gradient at the time. And along with these metasediments are suites of broadly granitic igneous intrusions which cut the fabrics and are not themselves responsible for the high temperatures recorded by the pegmatites. These intrusions were emplaced into already hot upper crustal rocks. So let's take a look.
It's a world of pegmatites. These are coarse-grained granitic rocks with large feldspars, some quartz in between, and large tourmalines. Granitic pegmatites. Well, it's tempting to think that the intrusion of granites weaken the crust, so make it more prone for deformation, and certainly a lot of deformed parts of the Earth's crust contain granite bodies like this, these coarse pegmatites. What matters is how long is this granitic material liquid. Then it can localize strain and be weaker than its surroundings. But if it's an aggregate of feldspar and even a fully crystallized granite, it's going to be way stronger than the surrounding materials. And if we skirt around these outcrops here, we can see evidence for that, of these granitic sheets behaving more competently than their surroundings.
So let's check out some of the pegmatite outcrops, look at their internal structure and how they relate to the metasediments into which they were intruded.
So these pegmatites, they're interesting. They've got weak deformation fabrics, but by and large they're pretty undeformed. They've still got really big crystals in them. They're essentially the original feldspars. That is almost a good pegmatitic texture. And they've got these little stringers that come out and are folded in the surrounding metasediments. And if you look carefully, these stringers, well, the feldspars are still sort of reasonably good crystal shapes. These have still got pegmatitic textures in them. So that's an interesting conundrum. It's one I've faced before. It's the pegmatite paradox. How is it these pegmatites have deformed and they've still got magmatic textures in them? And the answer is that they deformed while they were not fully crystallized. They've deformed as they were crystallizing. So synkinematic intrusion of pegmatite bodies. Really excellent.
But does this mean that the pegmatites, as they crystallized, were weaker than the surrounding rocks, which they need to have been if their intrusion weakened the crust? Let's go and look at another outcrop.
So, a pegmatite here intruded into the migmatites here, and you can see a wing of the pegmatite blobbing out like this. These are deformed relationships. Come in a bit closer here and you can see what I mean. Cuspate lobe geometries telling us that the pegmatite, when it was deforming, was more competent than the surrounding migmatites. Nice reaction rim around the edge of the pegmatite where it's interacted with the chemistry of the migmatitic metasediments. Really classic behaviours for deformation of competent versus less competent material. So the pegmatites are deforming, the country rock is also deforming as the pegmatites are coming in. And if you look at the main pegmatite here, we can see there's no shape fabric in it at all. It's a mass of large feldspars and some tourmalines around the edges in here. Feldspars are breaking up, so this is behaving rather like a sack of very coarse material that's just breaking and shattering as it achieves this deformation. So very competent coarse-grained pegmatites. So these pegmatites are blobby. They've pinched out. You can see that really nicely here on the margins of this big one, so that they've necked out as they've intruded. It's not simple boudinage. They've not been pulled apart after they've crystallized, because these have still got magmatic textures, but there's still deformation during the intrusion of the pegmatite bodies. Indeed, the last fractionates, which in this case are little quartz veins, localize in these sort of boudin-y necking structures. Well, not all the deformation in these pegmatites is before they were fully crystallized. This is a fantastic high temperature shear zone. It's really exquisite shear fabrics in here with the larger feldspars with these tails all strung out, defining this really intense shear plane parallel fabric. So intense deformation on the margin of this pegmatite. So deformation continuing after the crystallization of the pegmatites.
There's simply no significant evidence here of the pegmatite bodies ever being less competent than their surroundings. So the amount of time that high melt fractions existed was vanishingly small. These pegmatites just crystallized too quickly and so never contributed to weakening the deforming Variscan crust. But whatever, as here, the pegmatites behave more competently than their surrounding rocks, so have strengthened the crust. And deformation, although retarded, didn't stop. It just changed style. And Creus is famous for what comes next. Back to the country rocks.
Well, this area is made up of these metasediments, very steeply foliated here. But as we come down, we can see this steep foliation worked out into this gently dipping fabric going down like this, a later deformation. And it's these shear zones that Creus is really famous for. So this is our shear zone, the wall rocks, the steep fabric coming in like this, and just at the last minute it turns round into the shear zone here, and then what I'm standing on down in here is the other wall of the shear zone. So let's just follow up the fabric as it goes into the shear zone, and it comes up here. Fabric comes along here, it's a rather nice folding that comes round like that and out again, and on up and on up, on up, and eventually out into the other side of the shear zone. It's a really excellent shear zone, and then we can use this to get a sense of shear. But before we do that, let's just look down a little more detail at some of the other fabrics closer into the shear zone. So some really nice shear zone fabrics in here, where this fabric comes in like this and then swept out into this narrow zone here of more intense strain. We see the other behavior on the other side of this sort of pod where it gets sheared out. So we see the fabric intense here, slightly less intense, widely separated, then shearing into this zone in like this, all of which implies this sense of shear, which is right lateral.
Zooming in, the foliation shows variation in intensity, little micro shears which give this shear sense, the same as elsewhere in the outcrop. And we can represent all this on my field sketch. This is all right lateral shearing.
Well, following the shear zone along, and it's actually really narrow and intense here, and it's a really nice outcrop a bit further on to look at what's going on as a shear zone that processes the material from the wall rocks. So you can see just how narrow the shear zone is just here. A pegmatite on this side of the shear zone in here coming in, and down here, well, these are pegmatites with these leucosomes that have come round and then are swept into the shear zone, attenuating out to make the fabric. So let's take a closer look at that.
Here are the leucosome lenses sweeping into the shear zone, smearing out, making these streaky rocks. called Mylonites.
So what about the pegmatite? Well, these black lumps, these are tourmalines, really coarse grained, aren't they? Huge, bigger than my thumb. And we take them down into the shear zone. And we can see that they break up and just disaggregate. And we can see other ones in here just disaggregating as we pick up this intense fabric. The quartz and feldspars define the fabric, and the tourmalines boudinage and break. So a mixture of deformation mechanisms depending on which minerals we're talking about. So really intense localized shear, processing the rocks on either side to make this really intense foliation, and that's what's characteristic of shear zones the world over. And this is a really classic example.
There are quite a few of these shear zones at Creus. This is one of the broader ones, perhaps 4 meters across, with intensely strung out layering. These represent former migmatites and the granitic pegmatites, now barely recognizable through this deformation. These are Mylonites.
So actually, when you're in the middle of a big pile of sheared rock, the middle of a shear zone like this, it's quite difficult to understand which way it's gone. You might find a good lineation, but the shear sense, that might be more tricky. So the best place to look is on the shear zone margin to see what the bend-ins are doing. So let's try this. This is the shear zone. This is the shear zone wall. So here we go. Shear zone, really good platy fabric, and the bend in coming down like this. So clearly implies that shear sense. Top that way, plan view, that would be a right lateral shear sense, slightly thrusty, slightly reverse and right lateral.
These structures have been mapped out by Jordi Carreras. This is the shear zone I was just exploring, and it sits in a network of other shear zones. Now step back and look at the scale. The black streets are the shear zones, a great piece of structural mapping, which shows the network of shear zones at the Cap de Creus. So let's check out another shear zone.
So it's another one of our localized shear zones. What, it's about a metre, maybe half a metre wide. Pegmatite. Here, reasonably intact igneous textures, and then as we come down here, they break up and get smeared out, and everything gets sheared out like this as the pegmatite gets deflected into our shear zone like this. So right lateral shearing, sweeping it out over my shoulder, and we can see these really intense deformation fabrics in here. Really spectacular strain localization after the intrusion of this particular pegmatite. So I've got a question for you. How important are these narrow zones of intense deformation, shear zones? This particular one, it's got a really intense fabric. It's nice and narrow. I can take photographs of it. Many others have taken photographs of this shear zone before me. Localized strain. Structural geology has spent a huge amount of effort understanding these things. But this shear zone's probably only moved maybe 100 meters. It's enough to generate a shear strain in this of maybe pushing 200. It's a very high strain. But in terms of understanding the crustal deformation here, maybe this deformation is more important. It's penetrative. All these wall rocks have got really intense deformation. It's not as intense as the shear zone, and it's harder to photograph because it's everywhere. I've got a feeling that as structural geologists, we've spent too much time worrying about localization and not enough time looking at distributed strain when it comes to understanding the deformation of continental crust.
Understanding the relative significance of localized versus distributed strain is, I think, one of the frontiers of structural geology and mountain belt tectonics. And some of the evidence we need is available at the Cap de Creus. This is a semi-quantitative map of distributed strain and is another piece of exceptional structural mapping, this time by Elena Druget and colleagues, tracing fabrics and blobs of pegmatites using the pegmatite shapes to define bulk strain patterns. Let's try and put this together and qualitatively gauge the relative significance of distributed versus localized shearing. We'll deal with a plan view, here with no deformation. And the structure starts with highly distributed strain recorded by the pegmatites and the other metasediments. Regionally, work by Creus and Druget suggests that it was bulk left lateral transpression. As this progresses, pegmatites and other igneous rocks are intruded, making the crust stronger, and so deformation localizes onto shear zones before the whole system locks up and deformation stops or goes somewhere else. So most of the bulk deformation is by distributed strain. The shear zones are the terminal stages only. Effectively, the intrusions have killed off the deformation.
Well, that's a quick visit to Cap de Creus. It's a wonderful natural laboratory for structural geology. And by looking at the structure evolution, we can learn something about how deformation works in the continental crust. Now, what that means for the tectonics of this part of the Variscan, well, that's something else entirely. And I still think there's a lot of work that needs to be done to sort out that tectonic story. Well, I hope you enjoyed this tour of Cap de Creus, and I hope you can join me in another film that looks at the tectonic evolution of part of our world.